Welcome back to the virtual class of Milestone College. Dear students, today I am going to discuss about the characteristics of ideal gases and real gases. Students, before knowing characteristics of ideal gas and real gases, you have to remember about the Boyles Law. Now, I would like to show you Boyles Law shortly. Look at the whiteboard. According to the Boyles Law, all of you know that at constant temperature, the volume of a definite mass of a gas is inversely proportional to applied pressure. So here I can write V is equal to K1 by P. Here K is proportionalism constant. So I can write here PB is equal to K. From this equation, I can say at constant temperature, whatever the pressure, the volume will change in such a way that the multiplication of applied pressure and obtained volume will always constant. So, if I draw a graph P versus PV, students, and let the unit of pressure is 1 atm, and here this is the origin 0 0 1 2 3 4 5, and the values are PV is equal to 1 2 3 x axis and y axis. And if I do the experiment at constant temperature, then at 1 atmosphere pressure, suppose the value of PB is 2, so the coordinate will be here. And if the pressure is 3 atmosphere pressure, the volume will also like this. And if I measure the volume at 5 atmosphere pressure, the PB will also 2. I mean 2 is actually constant. This is just a number to make you understand easily, but it is not any experimental number. However, if you plot an experimental coordinate here, you will get also same type of graph here. However, students, now if I connect all those coordinates, I will get a parallel line to the x-axis. So I can say here this line is ideal gas line. This line is for ideal gas. I mean, if any gas give a parallel line to the x-axis, after plotting P versus PB at constant temperature, then we have to understand that the gas obeys Boyles Law, and at constant temperature in all pressures, if any gas follows Boyles Law, you have to understand that the gas is an ideal gas, but in reality it is not happening at normal temperature and pressure. So the scientist Amagat did an experiment on the real gases, and he got so many different curves for different real gases, and he got this type of curves, which curves are deviated from the ideal gas line. So it can be understood easily the real gases, which gases are around us, nitrogen, oxygen, hydrogen, those gases does not give any parallel line to the x-axis in this type of graph. So if I plot P versus PB at constant temperature for real gases, I will get this type of curve, and Amagat, scientist Amagat also got this type of graphs. This type of curve are known as Amagat curve. So what type of decisions can be taken from this Amagat curve? It proved that the real gases don't follow the gas law perfectly. They deviate from ideal nature. They deviate from the parallel line, ideal nature. This is first one. And second one, if temperature is too high, then the real gases behave as ideal gas. This means that the deviation from ideal behavior becomes less and less with increase in temperature. If temperature is high, then the volume of gas will high also. In that case, the gaseous molecules will go far from one another, and the intermolecular force among the gaseous molecules will be negligible. It is supposed that it seems that there is no intermolecular force among the gaseous molecules. That's why the real gases behave maximum like ideal gas. They shows ideal characteristics at high temperature, and also this type of phenomena is happening at low pressure also. The gases which don't follow the gaseous law perfectly are known as real gases. Students, I am sure that you have got the point about the real gas and ideal gas from this Amagat curve. So students, now I would like to show you the critical temperature, critical pressure and critical volume, which are very important for the liquefying of a gaseous substance. Critical temperature, students, if you apply pressure on carbon dioxide above 31.1 degree centigrade, it will never convert into liquid phase. It will never convert into the liquid state, because above 31.1 degree centigrade temperature, the gaseous molecules of carbon dioxide have high kinetic energy, and the molecules are staying so far from one another. In that case, after applying pressure, they will not come closer to convert into liquid carbon dioxide. But if you decrease the temperature at 31.1 degree centigrade or below 31.1 degree centigrade, then if you apply pressure, if you apply sufficient amount of pressure, then carbon dioxide gas will convert into liquid state. That's why 31.1 degree centigrade temperature is the critical temperature of carbon dioxide gas. Dear students, it is stated that if the value of critical temperature is high, then it is easy to liquefy a gas. But if the critical temperature is very low, if the critical temperature is below the freezing point, minus point, in that case it is very tough to convert any gas into liquid form. So it is noted that critical temperature also depends on intermolecular force. If intermolecular force is higher, the critical temperature is also higher. In that case, the gas can be liquefied easily. If the critical temperature is below freezing point, in that case, first I have to decrease the temperature of gas mechanically. Then I have to apply appropriate pressure. It is very tough to liquefy a gas if its critical temperature is below the freezing point. Now look at the critical pressure. Critical pressure. Students, if you consider again carbon dioxide at 31.1 degree centigrade temperature, if you apply 72.9 atmosphere pressure, then carbon dioxide gas will convert into liquid form. It means 72 atmosphere pressure is the critical pressure of carbon dioxide. It is stated that if you apply less than 72.9 atmosphere pressure, it will not convert into liquid form. So you may apply more than 72.9 atmosphere pressure. It's not a headache, but you can't apply less than 72.9 atmosphere pressure. So what will be the definition of critical pressure? The pressure which is required to liquefy a gas at its critical temperature is called critical pressure of that gaseous substance and critical volume. Now students, look at the critical volume. The critical volume of carbon dioxide is so 31.1 degree centigrade temperature and 72.9 atmosphere pressure, carbon dioxide occupy 95.65 ml volume. Here the amount of carbon dioxide is 1 mole. So students, I can say here the critical volume of carbon dioxide is 95.65 ml mole inverse. So what will be the definition of critical volume? The volume occupied by a certain mass of a liquid or gaseous substance at the critical temperature and pressure is called critical volume. Students, Now you have to know about the Joule Thomson effect. Now students, I am going to show you the Joule Thomson effect. If a compressed gas is suddenly expand, in that case the gaseous molecules will shift far distance from one another suddenly, and the temperature of gas becomes low. I mean, due to the decreasing of temperature, the gaseous molecules come closer and their kinetic energy is also decreased, and the intermolecular force among the gaseous molecules is also increased, and as a result the gas can be liquefied very easily. So I can say, by applying Joule Thomson effect, the gaseous substance can be liquefied very easily, and from the Joule Thomson effect we can realize that there is a intermolecular force among the gaseous molecule, and of course each of the gaseous substance has a specific temperature at which Joule Thomson effect is activated. This temperature is known as inversion temperature. Scientists Joule and Thompson did this experiment. That's why this experiment is known as Joule Thomson effect. Students, if I give you an example in our daily life, suppose perfume. If you spray perfume in our body, or if I spray body spray in our body, we feel cool because the perfume is compressed in the perfume container or perfume bottle, but when it comes out from the bottle through the spray, that time the perfume particles are spread out from and go far from one another. In that case work is done, and here the heat energy is used from the internal system of the perfume. That's why the energy is decreased and the perfume becomes cool and we feel cool after giving body spray in our body. Dear learners, now I am going to discuss about the reason of deviation of real gases from the ideal characteristics. Actually, there are two reasons for the deviation of the real gases from the ideal characteristics. Number one, volume defect, and number two, pressure defect. Dear students, all of you know that the ideal gas equation is actually PV is equal to nRT. During the reduction of PV is equal to nRT, it is supposed that the gaseous molecules have no volume of their own. The volume of the gaseous container is the volume of the gas molecules or gas, but in the Joule Thomson effect, all of you saw that the gas becomes into liquid. Even if it is cooled down at low temperature, that time it converts into liquid, even solid also. And that time it shows its own volume. So of course the volume of real gas will be V minus B. I mean the free movement area of real gas will be V minus B. It is applicable for 1 mole of gas. For 1 mole gas. But if I consider n mole of gas, the volume will be V minus NB for n mole gas. Dear learners, so I can say I have to use V minus NB instead of V for the real gas in this equation. Then pressure defect. Students, in the kinetic theory of gas, it is supposed that there is no intermolecular force among the gaseous molecules, but in really it is not happening. As the gas becomes into liquid state, even solid state, of course it has intermolecular force among the gaseous molecules, though it is absolutely negligible at normal temperature and pressure, but it is the fact that at high pressure and low temperature the intermolecular force among the gaseous molecules appears. So students, if I consider A and B are the molecules of a gas, and B gas apply pressure on the inner wall of the container. Suppose the applied pressure is P and the intermolecular force between the gaseous molecules is intermolecular force is actually activated against the pressure. So intermolecular force is actually a negative force. So students, the pressure applied by the B molecule is P, but due to the intermolecular force the pressure will be less. That's why I have to deduct the pressure, the intermolecular force from the applied pressure. It will be intermolecular force but the intermolecular force itself is a negative force. That's why the resulting term will be P plus intermolecular force. But for the intermolecular force, I can write here n square A by V square. This is a term for intermolecular force. So students, I can say here P plus n square A by V square can be written in state of P. So the resulting equation will be P plus n square A by V square into V minus NB is equal to nRT. This is van der Waals equation, and this equation is applicable for real gas. Dear learners, now you may ask me, sir, when the real gas will show the ideal characteristics? Yes, the real gas also shows the ideal characteristics, but those real gases show the ideal characteristics at high temperature and very low pressure. Dear students, you know that P plus n square A by V square into V minus NB is equal to nRT. This is the van der Waals equation which is applicable for real gas, but at high temperature the volume of the gas will also be higher. In that case, the gaseous molecules will go far in distance from one another, and here the volume V minus NB is near about V, because when the gaseous molecule will exist as an individual molecule, that time the volume of its own will be negligible. So, dear students, I can write here V minus NB is near about V. And again, at high temperature, when the gaseous molecule will exist far distance from one another, that time they will not feel any intermolecular force among themselves. In that case, the intermolecular force will be absolutely negligible. So, it will be P plus N square A by V square is near about P. So, dear students, at high temperature, the van der Waals equation converts into PV is equal to nRT. I mean, the real gas behaves like an ideal gas. And again, at low pressure, as well as at low pressure, the kinetic energy of gas will increase and the gaseous molecule go far distance from one another. In that case, the volume will be V minus NV is near about V, and also the intermolecular force becomes negligible. That's why the intermolecular force will be also P plus N square A by V square is near about P. So, I can say at low pressure, the van der Waals equation also converting to PV is equal to nRT. I mean, the van der Waals equation will also convert into the ideal gas equation. So, dear students, no more today and goodbye.